We're going to look at a problem from the 1968 International Math Olympiad. This is problem number 6, and it's a very interesting problem involving the floor function, or the greatest integer function. And what this problem says is, for every natural number n, we're given this infinite series, defined in terms of this series of floor function values, and we're asked to evaluate the sum. So before I show you the solution here, let's see if we can play around with this a bit and get a handle on what's going on. It's always a good idea to do that before you just jump in and try and start proving stuff. So when I look at these terms here, one thing I notice is I've got a half, 2/4, ... 2 to the k over 2 to the k plus 1, that's also a half. So each of these terms is really just the floor of something plus a half. So this seems that this is a very important quantity or function that I should be looking at. And actually, this has a name. This is a function that returns the nearest integer to x. So this is the nearest integer function. Now I need to be a little bit careful here. There is a bit of an ambiguity regarding how you deal with ties. So how you deal with, say, a number like 3.5. Do you round it down to 3? Do you round it up to 4? So this function right here is always going to round up. So when I say round up, I mean towards infinity. But with that convention, then this is always returning the nearest integer to x. So let's go back to our series here on the right. Given that the floor of x plus 1/2 is really just the integer that's closest to it, if n was really large, then really I could just kind of pretend that this was just n, right? So let's pretend that we didn't have this function here and we just tried to add up all these different terms. Let's see what we would get. So this first term, instead of being n over 2 plus a half, it would just be n over 2. So without the nearest integer function, then what we really have is n over 2 plus n over 4 plus n over 8 plus ... Now, you may recognize this as just a geometric series, and this just adds up to n. Okay, so that gives us a sense that whatever this is going to add up to, it's probably going to be close to n. It's going to be somewhere around there. Now, as it turns out, the solution here, I'll just tell you what the solution is. The solution does turn out to be exactly n, which is kind of interesting. So what it's saying is, if I were to add up this geometric series, I would get exactly n. But this is saying if I take those same terms and I take the nearest integer to each of those terms with the convention of rounding up, I'll also get n. Kind of an interesting result. It's not obvious why that is. What I'm going to show, though, is something a little bit more. It turns out that you don't really need to restrict n to be a natural number here. We could take n to be any positive real number or non-negative real number. So let's replace n with some x bigger than or equal to 0. Then what I'm going to show is that this sum, if I replace n with x, so that's x plus 1 over 2 plus x plus 2 over 4, and so on. This does not give me just x. And you can see why that is, because each of these terms are going to be integers. So there's no way that I could add up a bunch of integers and get just any real number. But it does add up to the floor of x. So if x happens to be a natural number n, then of course this is going to agree because the floor of that natural number n is just going to be n, which agrees with the solution to the problem. But we're going to show this more general statement here. Now I want to illustrate this with a particular value of x. So we're going to look at x equals 267.83. So the normal geometric series here would be, say, take half of this, and then take half of that, take half of that. So just keep taking half of these, and then add up all those infinitely many terms, and you'll get exactly 267.83. So what I'm going to do is take half, but what I'm going to do then is take the nearest integer to it, and then we'll calculate the nearest integer to those terms, add them up, and see that we get the floor of 267.83, which is 267. So here are the numbers I get if I repeatedly keep taking half over and over again. I'm going to get 133.915, 66.958, 33.479, 16.739, 8.37, 4.185. And so just note, if I keep taking half, I'm going to eventually get a number that's less than 1. So even though the sum in the problem is an infinite series, eventually those terms are just going to be 0. So for any fixed value of n, or for x, it's just a finite series. That's actually very common in number theory when you have these infinite sums, that for any fixed value you're evaluating, it just ends up being a finite sum. Okay, and then here's the last few. Okay, and then I take the nearest integer for each of these. So that's going to be 134. So I round up here. 30. Now here I'm going to round down to 33.479. That's just closer to 33. 16.7 is going to round up to 17. 8, 4, 2, 1. 0.523 just barely rounds up to 1, and then 0.262, of course, is 0, and everything from there on out, of course, is going to give me 0. So I just have these 9 terms here, and if I add them up, I get 1, 2, 3, 4, 8, 16. Okay, so that's 33, and that's 133. Yep, and they add up to 267, which is the floor of 267.83. Okay, so that's just kind of illustrating that this works for this particular number. So why does it work in general, though? That's what we're going to find out. So to show this, what I'm going to do is use a lemma, which is actually a particular case of a very important identity. And the lemma I'm going to use is this. It's going to say that the floor of 2x is equal to the floor of x plus the floor of x plus 1/2. And this is for any x bigger than or equal to 0. Now, why is this true? How can I go about showing this? Well, let's look at the left-hand side here. What is the floor of a number? The floor of a number is just the number of positive integers up to and possibly including that number. So I can write this. So this pound symbol just means cardinality. So just how many numbers are in this set. So it's the number of integers that satisfy this inequality. Okay, and that's just by definition. That's the definition of the greatest integer, or the floor function. And then I'm going to notice that, well, k, being an integer, is either going to be even or odd, but not both. So what I can do is kind of a double counting argument. I've already counted all these integers up to and including 2x. Now I'm going to count how many even ones there are, and then I'm going to count how many odd ones there are. And then the total of those two counts is going to have to be the same as this. So how many evens are there? Well, the number of even integers here is going to be the number of integers m such that 2m is positive and less than or equal to 2x. Because every even integer has the form 2m. And then I'm going to add to this the number of odds. Well, how many odds are there? Well, every odd integer has the form 2m minus 1. Now, you're probably used to it saying that it has the form 2m plus 1, which is true, but I can also say 2m minus 1. So that means if I want to count the odds, I can count all the integers m such that 2m minus 1 is positive and less than or equal to 2x. All right, now what I'm going to do is just play around with these inequalities. So if I take this first inequality here and I divide through by 2, then I get the number of integers m that are positive and less than or equal to x. Now, on the second inequality, I want to solve for m, so I'm going to add 1 and divide by 2. And when I add 1 and divide by 2, I'm going to get 1/2 less than m less than or equal to x plus 1/2. Now, what are these two things? Well, if I put these together, this first term right here is just saying count how many positive integers there are up to and including x. And by definition, that's the floor of x. But the second term is also saying count the number of positive integers up to and including x plus 1/2. Now you might say, well, wait a second, it's m bigger than 1/2. But that's really the same condition as saying m bigger than 0 because there are no positive integers between 0 and 1. So this is still counting all the positive integers up to and possibly including x plus 1/2. So that's the floor of x plus 1/2. And that proves our little lemma here. That the floor of 2x is equal to the floor of x plus the floor of x plus 1/2. Now, this is actually a particular case of an important identity involving the floor function. So on the next chalkboard, I will write that down, and that's going to be a homework problem for you. So this is your first homework problem, is to prove this identity. Which is called Hermite's identity. And it's an important identity involving the floor function. The floor function, you may be familiar with it mostly maybe from a calculus class where it's used a lot as kind of a counterexample for limits and continuity. But it's actually really important in a lot of other areas of math, especially number theory. It comes up a lot. So what this identity says is if x is bigger than or equal to 0 and n is a positive integer, then the floor of nx is equal to the floor of x plus the floor of x plus 1 over n plus the floor of x plus 2 over n, and so on, all the way up to the floor of x plus n minus 1 over n. And the hint here would be to just mimic the proof that I just gave, which was the proof for n equals 2. So there's just a slight modification you need to make here, and the argument runs through very similarly. But anyway, think about this problem and how you would go about proving it in a similar way. Okay, let's go back to our original problem. We have this. But we were looking at specifically this term. So the form of the identity we're going to use is the floor of x plus a half being equal to the floor of 2x minus the floor of x. And this is really what we want to use here. Because what we can do then is apply this identity to each term in the sum. So apply this to each term. And what's going to happen is we're going to get a nice telescoping series. Then we just have to make sure that the remainder goes to 0. And then it just kind of falls out. So let's look at how we can put that together. So we were looking at this infinite sum. The x over 2 plus a half, x over 4 plus a half, x over 8 plus a half, and so on. And the floor of each of these. If we apply our identity here, so remember what our identity said. It said that it was the floor of twice that. Well, twice x over 2 is going to be x. So that's going to be floor of x, and then minus floor of that. And then for our next term, it's x over 4. So twice x over 4 is going to be x over 2. And then minus floor of x over 4 plus ... And then let's say that we go up to the nth term here. So what would the nth term be? It'd be x over 2 to the n plus 1/2. And that will be the floor of x over 2 to the n minus 1 minus the floor of x over 2 to the n. So this is the nth partial sum of that series. We've got canceling. So we're going to get all of this stuff canceling. And we're just left with that term and that term. In other words, we have floor of x minus the floor of x over 2 to the n. Now, if we just look at this, we need to ask what happens as n goes to infinity here. This is going to infinity, but then x is fixed. So everything inside the floor here is going to 0. So this entire term here is going to go to 0. So this nth partial sum is going to just approach floor of x as n goes to infinity. And that just shows that the sum is equal to the floor of x, which is what we were trying to show. And that is the solution to the problem. Now, there is one other problem that I'm going to leave you with that is related to this. So this is a similar sum. So this is going to say that the sum from k equals 0 to infinity. And now, instead of having just a single term here, we're actually going to have a double sum. So this is going to be the sum from j equals 1 up to n minus 1. And this is for x, again, bigger than or equal to 0 and n, a positive integer. And we're going to be adding up here the floor of x over n to the k plus 1 plus j over n. And this is supposed to add up to floor of x. So notice that this is exactly the IMO problem, the competition problem, if n is equal to 2. Then it's the competition problem. So this is a very interesting result, and it's a generalization of the competition problem. So this is a really interesting result. So go ahead and see if you can figure out why this is true. Okay, I'll talk to you next time.